Welcome everyone. Today we're going to build a GPT, a Generative Pre-trained Transformer, completely from scratch, not using a library, not calling an API. We are writing every single component by hand, from raw text all the way to a model that generates coherent Shakespearean dialogue. This implementation follows the foundational ideas from the Attention is All You Need paper by Vaswani and colleagues, combined with the decoder-only architecture introduced in the original GPT paper by Radford and colleagues at OpenAI. By the end of this notebook, you will understand, at a deep mathematical level, how self-attention works, how transformer blocks are composed, and how a language model learns to predict the next token in a sequence. Let's get started. Every language model begins with data. For this demonstration, we use the tiny Shakespeare dataset, a single text file containing approximately 1.1 million characters from the complete works of William Shakespeare. We download it directly and load it into memory. After loading, we inspect the basic statistics. The dataset contains exactly 1,115,394 characters, which translates to roughly 1.12 megabytes. Now that might sound small, but for a character-level model on a single GPU, this is a perfectly reasonable training corpus. When we examine the first 1,000 characters, we see a distinctive structure. Character names like First Citizen appear on their own lines, followed by colons and then dialogue. There are also stage directions, line breaks, and punctuation. This structured format is actually a great test case. A successful model should learn not just English words, but also the formatting conventions of a play script. Before we can feed text into a neural network, we need to convert it into numbers. This process is called tokenization. We implement character-level tokenization, which means every unique character in our dataset becomes its own token. This gives us a vocabulary size of just 65 characters. That's lowercase and uppercase letters, digits, punctuation marks, spaces, and new line characters. Now, let me be clear about the trade-offs here. Character-level tokenization produces very long sequences but has zero out-of-vocabulary issues. In contrast, production models like GPT-2 and GPT-3 use Subword tokenization, specifically byte pair encoding, which compresses text into roughly 50,000 tokens. That's far more efficient for training. But for pedagogical purposes, character-level tokenization keeps things simple and transparent. We create two lookup dictionaries, one mapping characters to integers, and another mapping integers back to characters. We verify this with a round-trip test, encoding the string hello world into a sequence of integers, then decoding it back. The result matches perfectly. Our tokenizer is correct. Now we convert the entire text corpus into a single PyTorch tensor of token indices. This gives us a tensor with over 1 million elements, each being an integer between 0 and 64. We split this data into two sets, 90% for training and 10% for validation. The split is sequential. We simply take the first 90% as training data and the remaining 10% as validation. For language modeling, this is standard practice. We don't shuffle because we need to preserve the sequential structure of the text. Next, we introduce a critical concept, the context window, also called block size. Transformers have a fixed maximum context length. In our initial demonstration, we set this to 8, meaning the model can attend to at most 8 previous tokens when making a prediction. Here's the key insight. A single training chunk of length 8 actually contains 8 separate training examples, one for each position. At position 0, the model sees only one token and must predict the next. At position 1, it sees 2 tokens and predicts the third, and so on. This progressive context growth is fundamental to how autoregressive models learn. They must be good at prediction regardless of how much context they have. We use mini-batch stochastic gradient descent. Our batch function randomly samples starting positions from the dataset and extracts chunks of length block size. Each batch contains multiple independent sequences processed in parallel. This gives us the best of both worlds, the noise reduction of averaging over multiple examples, combined with the computational efficiency of parallel processing on a GPU. Before we build the full transformer, we start with the simplest possible language model, a Bigram model. This model predicts the next token using only the current token, no context whatsoever. Mathematically, a Bigram model estimates the probability of the next token given only the previous token, p of xt given xt minus 1. We implement this as a single embedding table of size vocabulary by vocabulary. Each token simply looks up its row in this table, and that row directly gives the logits, the unnormalized log probabilities, over all possible next tokens. When we initialize this model and check its loss, we get approximately 4.87. Now for a randomly initialized model with a vocabulary of 65, the expected loss under a uniform distribution would be the negative log of 1 over 65, which equals about 4.17. Our initial loss being slightly higher than this is expected. The random weights don't produce a perfectly uniform distribution yet. This is a good sanity check. We also generate text from this untrained model. As expected, it's complete gibberish. Random characters with no discernible pattern. Something like SR QP-QWK. Completely meaningless, but this gives us a baseline to improve from. We train using the AdamW optimizer with a learning rate of 1 times 10 to the minus 3 power. AdamW combines adaptive learning rates with proper weight decay. It's the standard optimizer for transformer models. Over 10,000 training steps, we watch the loss decrease from 4.70 down to about 2.50. That's a significant drop. The perplexity, which is a raise to the power of the loss, goes from about 110 down to 12. This means the model's effective uncertainty has been reduced from 110 equally likely characters to about 12. Now, let's look at what the trained Bigram model generates. It's still not English, but it's dramatically better than random noise. We start seeing common letter combinations, some short words, and character patterns that look vaguely language-like. For example, you might see fragments like the or and appearing occasionally. The model has learned which characters tend to follow which other characters, but without any broader context, it simply cannot produce coherent text. This is the fundamental limitation we need to overcome. This is the core of the transformer architecture, and I want to spend some time building the intuition carefully. The Bigram model fails because each token only looks at itself. What we need is a mechanism for tokens to communicate, to share information across the sequence. Self-attention provides exactly that. Consider a sequence of token representations. For each position t, we want to compute a weighted average of all previous positions. The result is a new representation for position t that aggregates information from its entire history. The weights must sum to 1, they must be non-negative, and, critically, each position must only attend to positions that come before it. This is the causal constraint that makes the model autoregressive. We developed this idea in 3 versions. Version 1 is a naive loop. For each position, we explicitly average all previous token representations. It works, but it's painfully slow. Version 2 replaces this loop with a matrix multiplication using a lower triangular matrix. A lower triangular matrix of 1s, when row normalized to sum to 1, gives us the exact same running average, but computed in a single parallelizable operation. When we compare the outputs, they match to numerical precision. Same result, massively more efficient. Let me explain why this works. The lower triangular structure enforces causality. Row 0 has a 1 only in column 0. Position 0 can only see itself. Row 1 has 1s in columns 0 and 1. Position 1 sees itself in the previous token. Row 7 has 1s in all 8 columns. It attends to the full context. After normalization, each row becomes a set of attention weights that sum to 1. Version 3 introduces softmax normalization. Instead of hard-coded uniform weights, we start with a matrix of zeros, mask the upper triangle with negative infinity, and then apply softmax. Negative infinity through softmax becomes exactly 0, enforcing the causal mask. Zeros through softmax become equal positive weights. The result is identical to version 2, but now, and this is the key, we can replace those zeros with learned data-dependent values. and that is exactly what self-attention does. Section 8. Scaled dot product self-attention. Now we arrive at the full attention mechanism as described in the original paper. For each token, we compute 3 vectors through learned linear projections. The query vector represents, what am I looking for? The key vector represents, what do I contain? And the value vector represents, what information do I provide if someone attends to me? The attention formula is elegant. We compute query times key transpose, scale by 1 over the square root of the key dimension, apply the causal mask, pass through softmax, and multiply by the values. In equation form, attention of Q, KV equals softmax of Q minus K transpose over root dk times V. Let me walk through the dimensions. With batch size B, sequence length T, and head size of 16, the queries and keys each have shape B by T by 16. The dot product Q times K transpose produces a B by T matrix. For each pair of positions, we get a scalar attention score. The scaling factor of 1 over root dk is crucial. Without it, when the head dimension is large, the dot products can become very large in magnitude. Large values push through softmax saturate to near 0 or near 1, essentially becoming a hard argmax. The scaling keeps the scores in a moderate range, where softmax produces well-distributed, informative attention weights. This is a subtle but critical detail for stable training. After scaling, we apply the causal mask, setting all upper triangular entries to negative infinity, and then softmax. The resulting attention weight matrix has a beautiful structure. The first row is all concentrated on position 0. Later rows distribute attention across all available positions with varying weights depending on content similarity. Finally, we multiply these weights by the value matrix. The output for each position is a weighted combination of the value vectors from all positions it attends to. Each token has now gathered information from its relevant context, and it learned which context is relevant through training. Now we assemble all the components into a complete GPT architecture. Let me first walk through the hyperparameters. We use an embedding dimension of 384, 6 attention heads, 6 transformer layers, a context window of 256 tokens, and a dropout rate of 0.2. For comparison, GPT-2 Small uses 768 dimensions, 12 heads, and 12 layers. GPT-3 uses 12,288 dimensions, 96 heads, and 96 layers. So our model is deliberately small, a pedagogical model, but it has all the same architectural components. Let me describe each component in order. First, the head class. This implements a single head of causal self-attention. It contains 3 linear projections for queries, keys, and values, a causal mask stored as a buffer, and dropout for regularization. Second, multi-head attention. This runs multiple attention heads in parallel and concatenates their outputs. With 6 heads and an embedding dimension of 384, each head operates on 64-dimensional subspaces. Different heads can learn to attend to different types of relationships. Syntactic structure in one head, semantic similarity in another. Third, the feed-forward network. This is a simple 2-layer MLP with a real U activation, applied independently to each position. The inner dimension is 4 times the embedding dimension, and so 384 times 4 equals 1,536. This follows the convention from the original transformer paper. The feed-forward network is where the model does per-token computation, processing the information gathered by attention. Fourth, the block class. Each transformer block combines multi-head attention with a feed-forward network using pre-norm layer normalization and residual connections. The forward pass is simple but critical. X equals X plus attention of layer norm of X. Then X equals X plus feed-forward of layer norm of X. The residual connections allow gradients to flow directly through the network, enabling training of deep models. The layer normalization stabilizes the activations. Finally, The GPT language model class ties everything together. It has a token embedding table, a positional embedding table, a stack of transformer blocks, a final layer norm, and a linear projection back to the vocabulary, the language modeling head. In the forward pass, we look up token embeddings, add positional embeddings, pass through all transformer blocks, apply layer norm, and project to vocabulary logits. For generation, we use autoregressive sampling, taking the logits for the last position, applying softmax to get probabilities, sampling the next token, appending it to the context, and repeating. When we instantiate this model and count parameters, we get approximately 10.8 million. Nearly 99% of those parameters reside in the transformer blocks. The embeddings are small because our character-level vocabulary is only 65 tokens. In GPT-2, with a vocabulary of 50,000 or more, the embedding layers would dominate. We train for 5,000 iterations with the AdamW optimizer at a learning rate of 3 × 10⁻⁴. We evaluate on both the training and validation sets every 500 steps. The results are striking. At step 0, the training loss is 4.22, close to the random baseline. By step 500, it has already dropped to 1.75. By step 1000, it's at 1.39. The model continues improving through step 3500, where the training loss reaches approximately 1.02. Meanwhile, the validation loss tells a complementary story. It drops quickly at first, reaching about 1.50 by step 1000, but then begins to plateau around 1.48 to 1.51. The growing gap between training and validation loss, from nearly 0 at the start to about 0.5 by the end, indicates the model is beginning to overfit. If we wanted to push further, we would need more data, more regularization, or both. Let's put these numbers in perspective. The Bigram model converged to a loss of approximately 2.5, which corresponds to a perplexity of about 12. Our GPT model achieves a validation loss of approximately 1.48, corresponding to a perplexity of about 4.4. That means the model's effective uncertainty has been reduced from 12 equally likely characters down to roughly 4 or 5. The transformer architecture, with its ability to attend to long-range context, provides a dramatic improvement over the simple Bigram baseline. Section 11. Text Generation. Now comes the moment of truth. We generate 2,000 tokens from our trained model, starting from a single new line character. The quality difference is immediately apparent. The generated text exhibits several remarkable properties. First, structural elements. The model has learned the formatting conventions of Shakespeare's plays. Character names appear in uppercase followed by colons. Dialogue is properly formatted with line breaks. Stage directions appear where expected. Second, language patterns. We see coherent English words, not random character sequences. The model produces Shakespearean. Section 11, Text Generation. Now comes the moment of truth. We generate 2,000 tokens from our trained model, starting from a single new line character. The quality difference is immediately apparent. The generated text exhibits several remarkable properties. First, structural elements. The model has learned the formatting conventions of Shakespeare's plays. Character names appear in uppercase followed by colons. Dialogue is properly formatted with line breaks. Stage directions appear where expected. Second, language patterns. We see coherent English words, not random character sequences. The model produces Shakespearean vocabulary, words like thou, hath, wherefore, and prithee. Grammatical sentence structures emerge naturally. Third, limitations. While locally coherent, the text lacks long-range semantic consistency. Characters might start a sentence with one idea and drift to another. Names may be invented or mixed up, but remember, this is a 10 million parameter model trained on 1 megabyte of text with character-level tokenization. The fact that it produces recognizably Shakespearean dialogue is remarkable. Let's recap what we've accomplished and the key insights from this implementation. We built 3 models of increasing complexity: a random baseline with a loss of 4.17 and perplexity of 65, essentially uniform noise, a Bigram model with a loss of 2.50 and perplexity of 12, capturing simple character-level patterns, and our full GPT model with a training loss of 1.07 and validation loss of 1.48, producing coherent structured text. The architecture consists of 7 critical components, each serving a distinct purpose. Token embeddings map discrete characters to dense vectors. Positional embeddings encode sequence position because transformers have no inherent notion of order. Self-attention allows tokens to communicate and share information across the context. MultiHead attention provides multiple parallel attention patterns, each learning different relationships. FeedForward networks perform per-token computation on the information gathered by attention. Layer normalization stabilizes training by keeping activations well-behaved. And residual connections allow gradients to flow through deep networks. The progression from Bigram to full transformer illustrates a deep principle. The Bigram model is limited to first-order statistics, which character follows which. Self-attention extends this to arbitrary range dependencies within a fixed context window. And by stacking multiple layers, the transformer builds hierarchical representations, low-level character patterns in early layers, word-level and phrase-level patterns in later layers. What we've built here is a miniature version of the exact architecture that powers GPT-2, GPT-3, GPT-4, and the entire family of modern large language models. The differences are purely in scale: more parameters, more data, more compute, and in engineering refinements like better tokenization, learning rate schedules, and distributed training. The core ideas are identical. For those looking to go deeper, I recommend the original papers. Attention is All You Need by Vaswani and colleagues from 2017, the GPT-1 paper from 2018, the GPT-2 paper from 2019, and the GPT-3 paper from 2020 by Brown and colleagues. Thank you for following along with this implementation. I hope this has given you a clear, mathematically grounded understanding of how generative pre-trained transformers work from the ground up.